Good afternoon to the chairs of this session and all the participants of Whispers 2023. Myself, Raghavendra N, working at National Remote Sensing Center of Indian Space Research Organization on the calibration and validation of satellite sensors and its data products. Now I am going to talk about the assessment of ResearchSat-2A LIS-3 radiometric calibration accuracy with near simultaneous Prisma data over Niger 2. This work was carried out as a common project with Italian Space Agency ASI. The contributing authors are Shanthisree, Raghavendra, Sarita, Giorgio, Patrizia, and Diodato. During my talk, I will be introducing you about the sensors involved in this study site, cross calibration, assessment methodology, datasets selected for the study, and finally the outcomes of the study. Here I will introduce to you about two sensors involved for the study. They are LIS-3 of ResourceSat-2A mission and hyperspectral sensor of Prisma mission. ResourceSat-2A mission is the follow-on mission to ResourceSat-2 launched on 7th December 2016 for resource monitoring applications. It carried three multispectral sensors, namely EVIFS, LIS-3 and LIS-4 with ground sampling distances of 56 meter, 23.5 meter and 5.8 meter respectively. Out of all the three sensors, EVIFS has the largest swath of 740 kilometers with a revisit period of 5 days. Figure on the right shows the unique three-tier imaging concept of ResourceSat series. Using this concept, we can have common area in three different resolutions. The center picture shows LIS-3 multispectral sensors. It has 4 spectral bands covering visible to shortwave infrared regions. The spectral response of the 4 bands is shown in the bottom figure. The area imaged by LIS-3 sensor is mapped to a predetermined tile, which is designated by a path number and a row number. Path numbers increase from west to east and rows from north to south. Here, for example, the complete Jammu and Kashmir state in India is covered in 36 different tiles given by their path numbers and their row numbers. The other sensor which we will discuss is the hyperspectral sensor on Prisma satellite. Prisma satellite was also launched in the year 2016. This hyperspectral sensor images the Earth's surface in 237 different bands covering 400 to 2500 nanometers at a spectral resolution better than 12 nanometers and ground sampling distance of 30 meters. The pictures on the right side show the Prisma satellite and the imaging instrument. Study area selected for this work is a PIC site. PIC stands for Pseudo-Invariant Calibration Site. Certain sites or areas on the Earth's surface have specific characteristics such as they are spatially uniform and at the same time they are large in size. They are stable over long periods of time, have very high reflectance or brightness. They also have minimum vegetation and atmospheric influence. Areas with these characteristics are found in arid zones such as Saharan deserts. Left bottom picture shows the locations of PICs in North Africa. The red dotted box shows the location of Niger 2. Its coordinate and spatial extent are shown in the next picture indicated by a blue box. The table on the right side indicates the surface reflectance and its variability at 3 different wavelengths. The variability is shown to be better than 3%. In the cross calibration, the idea is to transfer the calibration from the reference sensor to the sensor under test. The transfer is effective if the imaging conditions like date and time of imaging, illumination and viewing conditions are identical to the reference and test sensor. As illustrated in the picture, if 3 sensors are imaging the same area, treating one sensor as reference, the other 2 can be calibrated against it. Here, in the present study, Prisma is considered as the reference sensor and LIS3 as the test sensor. Coming to the methodology part, Prisma level 1 datasets were downloaded from the archive. Later, the image statistics were extracted from 2 km by 2 km area around the Niger site. Further, the digital numbers were converted to top of atmosphere radiances and reflectance using appropriate scaling factors. Later, the hyperspectral top of atmosphere reflectance was integrated to generate multispectral reflectance equivalent to LIS3 bands. On the other hand, level 2 datasets of LIS3 sensor were downloaded from Boonidhi website. Digital numbers extracted from the Niger 2 site were converted to top of atmosphere using the scaling factors. Finally, the calibration ratios were generated by dividing the LIS3 top of atmosphere reflectance with Prisma derived multispectral reflectance. If the two values are close, the ratio should tend to unity. This slide shows the formulations used to generate top of atmosphere reflectance from Prisma data and LIS3 data. The process chains implemented are shown on the slide. The left part of the slide shows the Prisma data process chain and right side shows the LIS3 data process chain. The data process chain starts with digital numbers and then their conversion to radians to reflectance using sun zenith angles, E-sun values and sun-earth distance. For the Prisma case, the TOI reflectance generated is a hyperspectral reflectance. In order to compare with multispectral reflectance as in the LIS3 case, the hyperspectral reflectance has to be converted to multispectral reflectance. This was done using the band integration method. The hyperspectral reflectance was integrated across the bandwidths of LIS3 bands, and a multispectral TOA reflectance equivalent to LIS3 sensor was generated. Finally, the multispectral reflectances generated were used to generate the calibration ratios. This slide shows the datasets selected for the analysis. The datasets are spread across 3 years with 1 sample per year. The date of imaging, imaging time and the illumination conditions are near identical, which is a very important criterion for doing the cross calibration. This slide shows the color composite images of Niger 2 site. The image in the left picture is by LIS3 sensor and the right image is by Prisma. The small yellow boxes in both images show the region of interest selected for analysis. Pictures on the left side of the slide show the responses from Prisma and LIS3 sensors. The temporal response in each case were very close to each other, indicating a very good radiometric stability over 3 years. But as the hyperspectral measurements cannot be readily compared to multispectral measurements, hyperspectral measurements of Prisma were integrated in LIS3 spectral bands to derive equivalent multispectral response. The band integration is shown on the top right plot, and the multispectral response derived after integration is shown in the bottom right plot. Having multispectral top of atmosphere reflectance values from both the sensors, band-wise calibration ratios were determined. Mean and median values of the ratios are shown in the box plot along with the ideal value of 1. The mean ratios of all the bands were seen to be better than 0.95 except band 3, indicating good radiometric accuracy. Band 3 has a ratio of about 0.92, pointing some amount of corrections to be implemented. Further, the validation was done using the ground truth measurements made in the artificial calibration site. Artificial calibration site is located at one of the campuses of NRSC, 70 kilometers from Hyderabad. At this campus, data from different satellites of ISRO are received and processed. Artificial site is located in the same campus, built with 5 natural materials. The spectral response values of the 5 natural materials are shown in the top right plot. The calibration ratios determined using the ground measurements on red soil from the year 2017 to 2021 closely match with the ratios shown in the previous slide. Conclusions of the study are as follows. Near coincident image pairs of Prisma and LIS3 provide good opportunity for radiometric assessment. Measurements from both sensors are temporally stable. LIS3 measurements are in close agreement with Prisma. I conclude my talk by expressing wholehearted thanks to our director and other senior officials for constant encouragement and guidance. I also express my sincere thanks to the reviewers of the paper and the organizers for giving me the opportunity. Thank you.